Welcome to DAR Tutors, your trusted source for online and home tuition. Today, we're diving deep into a key topic for your IB applications and interpretation higher-level exams: nonlinear modeling. Linear regression, which you are likely familiar with, is a powerful tool. But what happens when the relationship between two variables is clearly not a straight line? That's where nonlinear modeling comes in. By the end of this video, you will be able to perform logarithmic, exponential, and power model regressions using transformations, and you will learn how to choose the most appropriate model for a given dataset. You will also understand the fundamental principles behind nonlinear regression. So let's begin. Let's start with a classic opening problem. The higher a person is above the Earth, the further they can see. We have a table showing the distance a person can see, d, in kilometers, from a certain height, h, in meters. Notice the data shows that as the height h increases, the distance d also increases, but not in a straight line. To visualize this, we can plot a scatter diagram. As you can see, the points form a smooth, upward curving shape, but the rate of increase slows down. This is clearly a nonlinear relationship. When data is nonlinear, fitting a straight line to it would be inaccurate. So, our goal in nonlinear modeling is to find a nonlinear function that best describes this curve. But how do we find such a function? The primary method we'll use is called data transformation. The idea is to transform one or both of our variables, x and y, in such a way that the relationship between the new transformed variables is linear. We can then use standard linear regression on this transformed data, which we know how to do. In this chapter, we will focus on three common types of models: logarithmic, exponential, and power models. Each corresponds to a different type of data transformation. First, let's explore logarithmic models. A logarithmic model has the general form y equals a plus b times the natural logarithm of x. This equation is clearly not linear in x and y. However, let's make a clever substitution. If we let capital X equal the natural logarithm of lowercase x, then our model becomes y equals a plus b times capital X. This new equation, y against capital X, is a perfectly linear relationship. This is the core concept of a logarithmic model transformation. If the variables x and y are connected by a logarithmic model, then the graph of y against the natural logarithm of x will be a straight line. Visually, you might have a scatter plot of y against x that looks like this curving downward. But when you plot y against the transformed variable, the natural logarithm of x, it straightens out into a line. This linearity confirms that a logarithmic model is appropriate. So the strategy is, calculate the natural logarithm of all your x values, and then perform linear regression on the new points, where y is the dependent variable and ln x is the independent variable. The resulting linear equation will directly give you the coefficients a and b for your logarithmic model. Let's work through an example. Suppose a graph of y against the natural logarithm of x is linear, and we are given 2 points on this line. The graph shows a line passing through the points as 0, 0.5, and 4, 1. Remember, the horizontal axis is ln x. Because the graph is linear, we know we can find a simple linear equation to connect y and ln x. This equation is of the form y equals m times ln x plus c, where m is the gradient and ce is the y-intercept. First, the gradient. The gradient m is the change in y divided by the change in ln x. Using our 2 points, that's 1 minus 0.5, divided by 4 minus 0, which equals 0.5 over 4, or 0.12. The gradient tells us the coefficient b in our logarithmic model. Next, the y-intercept. The line passes through the point where ln x is 0, which is the y-axis. From the graph, we can see the line intersects the y-axis at 0.5. So, our y-intercept c is 0.5. This gives us the coefficient a in our model. Putting it all together, the linear model connecting y and ln x is y equals 0.125 times ln x plus 0.5. And that's our logarithmic model. We've used the property of data transformation to fit a nonlinear model by analyzing a linear graph. Next, let's turn our attention to exponential models. An exponential model has the form y equals k times b to the power of x, where k and b are positive constants. Again, this is clearly nonlinear. To transform it, we'll use a property of logarithms. We take the natural logarithm of both sides of the equation. This gives us the natural log of y equals the natural log of k times b to the power of x. Using the logarithm property that the log of a product is the sum of the logs, we can split the right side into the natural log of k plus the natural log of b to the x. Then, using another property, we can bring the exponent x down, resulting in the natural log of k plus x times the natural log of b. Now let's rearrange it slightly. This looks like a linear equation. If we let capital Y equal the natural log of lowercase y, and let capital X equal lowercase x, then our equation becomes capital Y equals the natural log of k plus capital X times the natural log of b. This is a linear equation in the form y equals mx plus c. The gradient m is the natural log of b, and the y-intercept c is the natural log of k. So, if your data follows an exponential model, plotting the natural log of y against x will produce a straight line. By finding the gradient and intercept of this line using linear regression, we can find the constants k and b and determine the exponential model. Let's work through an example of an exponential model. Suppose we have a graph showing the natural logarithm of y against x. The graph shows a line that intersects the y-axis, or ln y-axis, at 4 and passes through the point 8, 10. First, we calculate the gradient. The gradient m is the change in ln y divided by the change in x. That's 10 minus 4 divided by 8 minus 0, which is 6 over 8, or 0.75. This value is equal to the natural log of b in our model. The y-intercept c is where the line crosses the vertical axis. In this case, it's given as 4. This value is equal to the natural log of k. So the linear equation for our transformed variables is ln y equals 0.7x plus 4. But we need the exponential model in terms of y and x. To do this, we need to rearrange the equation to make y the subject. We will exponentiate both sides using e as the base. E to the power of ln is just y. So y equals e to the power of 0.75x plus 4. Using an exponent rule, we can rewrite this as e to the power of 0.75x times e to the power of 4. We can also write this as e to the power of 4 times the quantity, e to the power of 0.75, all raised to the power of x. This is now in the form y equals k. Calculating e to the power of 4 gives approximately 54.6, and e to the power of 0.75 gives approximately 2.12. Therefore, our exponential model is y approximately equals 54.6 times 2.12 to the power of x. We have successfully transformed the linear relationship back into the original nonlinear form. Our third type of model is the power model. A power model has the form y equals a times x to the power of n, where a is a positive constant and n is any non-zero constant. Notice that the variable x is in the base, and the exponent n is a constant, which is the opposite of an exponential model. The transformation for a power model involves taking the natural logarithm of both sides, just like with the exponential model. The natural log of y equals the natural log of a times x to the power of n. Using the same logarithm properties, we get the natural log of a plus n times the natural log of x. Now let's look at this carefully. We have the natural logarithm of y on one side and the natural logarithm of x on the other. If we let capital Y equal ln y and capital X equal ln x, the equation becomes capital Y equals n times capital X plus the natural log of a. This is a linear equation. This means that if your data follows a power model, plotting the natural log of y against the natural log of x will give you a straight line. The gradient of this line will be the power n, and the y-intercept will be the natural log of the constant a. A special consideration for power models. Because we cannot take the logarithm of 0, any data point where x or y is 0 must be excluded from our analysis. Let's demonstrate this with an example. Suppose a graph of the natural log of f against the natural log of t is linear. We have a line that intercepts the vertical axis ln f at 0.6 and passes through the point 3, 6.6. First, the gradient. The gradient m is the change in ln f divided by the change in ln t. This is 6.6 minus 0.6 divided by 3 minus 0, which gives us 6 over 3, or 2. In a power model, the gradient of the transformed plot is the exponent n. The y-intercept c is where the line crosses the vertical axis, which is 0.6. The y-intercept of the transformed plot is the natural log of the constant a. So, the linear model connecting our transformed variables is ln f equals 2 ln t plus 0 points. Now we transform this back to the original variables f and t by solving for f. We can use logarithm properties to simplify the right side. Using the power rule for logarithms, we can write 2 ln t as the natural log of t squared. We can also express 0.6 as the natural log of e to the power of 0.6. Now, using the product rule, the sum of two logs is the log of their product. So, the natural log of f equals the natural log of t squared times e to the 0.6. Finally, we exponentiate both sides with base e to remove the logarithms. F equals e to the 0.6 times t squared. Calculating it to the 0.6 gives approximately 1.82. Therefore, the power model is f approximately equals 1.82 times t squared. We've successfully derived a power model from a linear graph of transformed variables. So we've learned three methods for transforming data: logarithmic, exponential, and power. But how do you know which one to use for a new dataset? This brings us to the general problem-solving strategy for nonlinear modeling. The goal is to determine whether a linear, logarithmic, exponential, or power model is most appropriate for a given set of x and y variables. Step 1 is the most crucial. Draw all four scatter diagrams. Plot y versus x, y versus lnx, lny versus x, and lny versus lnx. Visually inspect these four graphs. In most cases, one of them will appear significantly straighter than the others. That linear-looking plot tells you which model is appropriate. Step 2. Find the regression line for any scatter diagram that appears linearly related. Modern graphics calculators can do this quickly. The calculator will provide the equation of the line in the form ax plus b and, very importantly, a coefficient of determination, r squared. The coefficient of determination, r squared, is a measure of how well the regression line fits the data. Its value is between 0 and 1, and a value closer to 1 indicates a stronger linear relationship. If two or more models appear equally plausible from the scatter plots, you should choose the one with the highest r squared value. This model provides the best fit to the transformed data. Step 3. Once you have the linear model for the transformed variables, rearrange it to make y the subject. This final equation will be your nonlinear model connecting e and x. This systematic approach allows you to determine and fit the best possible nonlinear model to your data. Now that we've covered the transformation methods, let's address an important topic in IB mathematics: nonlinear regression. Sometimes, we cannot transform a nonlinear model into a linear one. A classic example is a quadratic model in the form y equals ax squared plus bx plus c. If we try to transform this with logarithms, the bk and c terms prevent it from linearizing. In such cases, we must use nonlinear regression. The principle of nonlinear regression is the same as linear regression. We want to find the curve that best fits the data. The way we measure best fit is by minimizing the sum of the squared residuals, or SREs. A residual is the vertical distance between a data point, I, and the corresponding point on the fitted curve, y hat I. The sum of the squares of these residuals gives us a value that quantifies the total discrepancy between the data and the model. Visually, if we have a set of data points and a quadratic curve, the residuals are the vertical distances from each point to the curve. Our goal is to find the specific values of the coefficients a, b, and c that make the sum of these squared distances as small as possible. For linear regression, we have simple formulas to find the coefficients. For nonlinear regression, like a quadratic or cubic model, no such simple formula exists. Instead, we use numerical methods. Your graphics calculator is equipped with these numerical methods. It can fit quadratic, cubic, and quartic models directly to data. When you use your calculator's quadratic regression function, you are performing a nonlinear regression calculation. This is a very powerful and practical tool in data analysis. So, Which is better, transformation and linear regression, or direct nonlinear regression on your calculator? The answer depends on the model. For power, exponential, and logarithmic models, transformation works perfectly. It gives us an exact linear fit and simple formulas for the coefficients. However, for polynomial models, such as quadratic or cubic, transformation is not an option. Here, your calculator's regression functions are essential. They use a numerical method to find the best fit, and this is typically what you will do in an exam. An interesting point of discussion. When your calculator performs quadratic regression, it is still technically using linear regression in a clever way. Consider the model y equals x squared plus bx plus c. If we let a new variable z equal x squared, the equation becomes y equals a's plus bx plus c. Your calculator treats z as another independent variable and performs a multiple linear regression, which is still a linear process. The key is that it's linear in the coefficients, a, b, c, even if it's nonlinear in the variable x. This is a subtle distinction, but it highlights why calculators are so adept at fitting these models. In practice for your IB exam, if you need to fit a quadratic or cubic model, you will simply use the built-in function on your graphics calculator. We've now covered all the main theoretical components. We can transform data for logarithmic, exponential, and power models, and we can use a calculator for polynomial models. You are now prepared to tackle any nonlinear modeling problem in the IB AI-HL syllabus. For expert tuition in IB A-Level and IGCSE curricula, please contact DAR Tutors. Our specialist tutors provide personalized support to help you achieve your academic goals. Now, let's consolidate our learning with some IB-style practice questions. A key skill is to identify the most appropriate model based on data, and then to use your calculator to find it. Here's the first question. Question 1. A company sells a new type of smartphone. The table below shows the number of smartphones sold each week for the first 8 weeks. We need to find the appropriate nonlinear model and use it to predict sales in the 12th week. Solution for question 1. First, we must identify the most appropriate model. We'll use our strategy of transformation. Using a calculator or spreadsheet, calculate the transformed variables, the natural log of the week number and the natural log of the sales number. Now we create scatter plots for all 4 pairs of variables and find their R-squared values. Plotting sales versus the week number shows a clear upward curve. A logarithmic plot of sales versus ln week is also curved. A power plot of ln sales versus ln week shows some linearity, but the best fit comes from the exponential model, ln sales versus the week number. The R-squared value for the exponential model, LS against W, is approximately 0.9998, which is very close to 1, indicating a strong linear relationship. This is higher than for the power model, which had an R-squared of around 0.994. Therefore, an exponential model is most appropriate. Next, we find the linear regression line for LNES against W on our calculator. The calculator gives us the equation LMATM ACS equals approximately 0.468 W plus 2.628. Finally, we transform this back to find the exponential model for sales. We exponentiate both sides with base e. This gives S approximately equals e to the power of 2.628 times e to the power of 0.468 TDU. Calculating the constant term, our model is S approximately equals 13.88 times 1.60 to the power of W. To predict sales in the 12th week, we substitute W equal to 12 into our model. S is approximately 13.88 times 1.60 to the power of 12. This gives a value of approximately 2,200 smartphones. This model suggests strong sales growth. Question 2. The population of a certain species of fish in a lake is monitored for several years. We need to find the power model for population P as a function of time t, and then use it to estimate the population in the year 2020. The question specifies a power model, but even if it didn't, a scatter plot of P against T would show an upward curving trend, and you would find that plotting ln P against ln T results in the best linear fit. To fit a power model I equals a times x to the power of n, We transform the data by taking the natural log of both variables. We'll use years since 2000 for t. Our transformed table will have columns for t, ln t, p, and ln p. For example, the first point, 2005-25, becomes a new point, 3.41, on the ln p versus ln t graph. Now we perform linear regression on ln p and ln t. Our calculator gives us a gradient n of approximately 1.815 and a y-intercept c, which is ln a, of approximately 0.285. The r-squared value of 0.997 confirms this is an excellent fit. Now we transform back. P equals e to the power of 1.815 ln t king t plus 0.285. Using logarithm rules, this simplifies to p equals e to the 0.285 times t to the power of 1.815. Calculating e to the 0.285 gives approximately 1.33. So our power model for the fish population is p approximately equals 1.33 times t to the power of 1.815. Finally, we predict the population in 2020. This corresponds to t equals 20. Substituting t equals 20 into our model, we get p approximately equals 1.33 times 20 to the power of 1.815. This calculates to approximately 277.6 thousand fish. Question 3. A cup of coffee is left to cool in a room where the temperature is 20 degrees Celsius. The table shows the temperature difference D in degrees Celsius between the coffee and the room at various times t in minutes. We need to find an appropriate model for this data. Let's follow our three-step process. Step 1. Draw scatter diagrams. Plotting D against T shows a curve that decreases rapidly and then levels off, which is characteristic of exponential decay. The scatter plot of ln D against T appears to be the straightest. Step 2. Calculate r-squared values for all four transformed pairs. The highest r-squared value, approximately 0.996, is found for the exponential model. D versus T. This confirms our visual assessment. Therefore, an exponential decay model is the most appropriate. Let's find the regression equation. We perform linear regression on the points t, ln, d. The calculator gives the equation ln d equals approximately negative 0.17 ecad plus 4.316. Transforming back to an equation for d, we exponentiate both sides. D equals e to the power of negative 0.87 at plus 4.316. This simplifies to d equals e to the 4.316 times e to the negative 0.1 at. Calculating e to the 4.31 gives approximately 75.09. Our final exponential decay model is d approximately equals 75.09 times e to the power of negative 0.178. The model fits the data very well. For example, when t is 0, the model predicts d is 75.09 degrees Celsius, which is very close to our data point of 75. This indicates a good fit at the start of the process. Question 4. A company's revenue, R, in hundreds of thousands of dollars, is modeled by a quadratic function of the number of years, T, since the company was founded. We need to find this quadratic model and predict the revenue in year 10. The problem states the model is quadratic, so we will use the quadratic regression function on our calculator. A scatter plot of revenue R versus time T shows a parabolic shape, reaching a peak around year 6 and then falling, confirming that a quadratic model is appropriate. We input the data into our calculator's statistical lists and select the quadratic regression tool, often labeled QuadReg. The calculator returns the coefficients for the model in the form y equals x squared plus bx plus c. We find AL is negative 0.25, B is 3, and C is 0. This means our quadratic model is R equals negative 0.25 squared plus 3t. To verify the fit, we can calculate the sum of squared residuals, SREs. The residuals are the differences between the actual revenue and the revenue predicted by our model. The residuals for this model are all 0. This tells us the model passes exactly through every single data point, a perfect fit. This is quite rare with real-world data, but it can happen with small, carefully chosen datasets. Let's recalculate the SREs. The residuals are actually all 1. The sum of the squared residuals is 5 times 1 squared, which is 5. So the fit is not perfect, but it's still quite good. The r-squared value would be very close to 1. Finally, we predict the revenue in year 10. Substituting t equals 10 into our model, we find r is $500,000. So the predicted revenue is $500,000. Last question for our review. The force of gravity, F, between two objects is recorded at various distances. D. We need to find the inverse model that connects F and D. Newton's law of universal gravitation is a classic example of a power model, specifically an inverse square law. It states that force is proportional to the inverse square of the distance. This means the model should be of the form F equals K divided by D squared, or F equals K times D to the power of -2. This is a power model where the exponent n is 2. To linearize this power model, we take the natural logarithm of both sides. This gives us the natural log of F equals -2 times the natural log of D, plus the natural log of K. So we should plot ln F against ln D and expect a straight line with a gradient of 2. Let's create our transformed data table. We calculate the natural log of F and D for each data point. Now, we use our calculator to perform linear regression on ln F against ln D. The calculator gives a gradient n of 2, which perfectly matches the theoretical value. The y-intercept c, which is ln k, is approximately 2.485. To find the model for F, we exponentiate both sides. F equals e to the power of -2 ln D plus 2.485. This simplifies to F equals e to the 2.485 times D to the power of -2. Calculating e to the 2.485 gives us approximately 12 Hd. Therefore, the force F is approximately 12 Hd divided by D squared. This model matches the theoretical inverse square law and confirms that our transformation method works perfectly for physical laws described by power models. We have now reached the end of our session on nonlinear modeling for IBAIHL. We started by understanding why linear models aren't always sufficient and introduced the powerful tool of data transformation. You now know how to recognize, transform, and fit logarithmic, exponential, and power models to data. You also understand the core principle of nonlinear regression using your calculator for polynomial models. The key is the problem-solving strategy. Create the 4 transform scatter plots. Identify the one that is most linear. Use your calculator to find its r-squared value, and then find the linear equation before transforming it back to the original variables. The more you practice this method, the more confident you'll become in applying it to various real-world scenarios, which is at the heart of the IB Applications and Interpretation syllabus. For expert tuition and personalized learning tailored to your specific needs, remember to contact DAR Tutors. Thank you for watching, and good luck with your studies.